So now we discuss the Gaussian random variable. So the probability density function for Gaussian random variable is mathematically defined as this particular expression. So probability density function Pxx is given by 1 by root 2 pi e to the power minus x square by 2. So remember that this is the this particular Gaussian random variable or Gaussian distribution is known as the standard Gaussian or standard normal distribution function or unit normal distribution function. So if we plot this function with respect to the Gaussian random variable x, then we are going to get this particular curve. So here we can see that, and this is e to the power minus x square by 2. So when we substitute for the values of x, then when this x equals to 0, we are going to get its maximum value, and that maximum value will be equals to 1 by root 2 pi. So this is our maximum value. And after that, if we substitute x greater than 0, in that case, this exponential function is going to decrease. Okay, and therefore this curve is actually decreasing. So once this x will become infinity, then this particular curve will be approaching towards 0. Similarly, if we substitute the negative values of x, then again, because it is x square, we are going to get a similar curve, but it will be approaching towards 0 when this x will become minus infinity. Okay, so this type of symmetrical probability density function curve we are going to get for Gaussian distribution. So now, if this is the PDF curve, we can also get its cumulative distribution function, right? So cumulative distribution function we can get by integrating this probability density function from minus infinity to x. So that will be given by this particular expression. Okay, so this particular integration is for your cumulative distribution function. So now here you can, you already know that this cumulative distribution function fxx represents that what is the probability that this random variable x will be less than or equal to x. So normally integrating or getting the analytical expression of this particular integration is very difficult, and therefore normally what we do is we go for the numerical integration process. So in the numerical integration process, we have another function which is known as the Q function. So normally we use the Q functions table, okay, to calculate this cumulative distribution function fxx. So there will be a relationship between the cumulative function fxx with your Q function. Okay, so here we see what is the definition of the Q function. So the Q function is actually defined by this particular expression. Here you can see it is 1 by root 2 pi, and this integration is going from y to infinity e to the power x square minus x square by 2 dx. So here you can make this comparison. Okay, this cumulative distribution function and this Q function both are similar integration. Okay, the only difference is that here the integration limit is going from minus infinity to x, and here this integration limit is going from y to infinity, and both are actually defined for your standard Gaussian. Okay, standard Gaussian function. So here, if you make a comparison, this cumulative distribution function represents the probability that this random variable x will be less than or equal to x, whereas this Q function represents that what is the probability that this random variable x will be greater than y. Okay, so because this integration limit is going from y to infinity, okay, and therefore this will be the probability. So this means that if you see this Q function, this means that we are actually interested in the area under this particular shaded curve. Okay, so this is our curve. So this is our shaded area. Okay, so this area represents this particular probability because we are integrating this PDF from y to up to infinity. Okay, and therefore this particular area represents the probability, right? So now one more point that we can understand from this curve itself is that, so because this PDF curve is symmetrical about the origin. Okay, so here you can see that this particular curve is actually situated around 0 and it is symmetrical about 0. Okay, so because it is symmetrical about 0, one thing which is very much clear that if we have any like value of x, here you can see we are having 1, 2, 3. Okay, so these are the different values. So if we are calculating any probability that the x is greater than y, then there must be a certain corresponding and negative values of x. Okay, that will be here and it will be minus y. Okay, as you can see, it is 1. Here we have x equals to -1. Here it is 2, it is -2. Similarly, we can also have a point here which will be minus y. Okay, so if I calculate what is the probability that this x will be less than minus y, then it is corresponding to calculating this area. Okay, and because of the symmetry of the curve, whatever be the area greater than y here, okay, will be same as the area which will be less than minus y. Okay, and this way we are going to get the same probabilities, right? So here, due to the symmetry that we can see, okay, so here you can see this q function curve. Okay, so this q function curve is actually, this we can understand from this curve, means this definition itself, that if we are having this q equals to infinity. Okay, so if q equals to infinity means if we integrate this particular curve from infinity to infinity, what will be the probability? Okay, so if we substitute infinity, it means that what is the probability that this random variable x will be greater than infinity. So there is no such probability. Okay, because this random variable cannot take any value which is greater than infinity, right? And therefore this probability is going to be 0. So therefore I have written over here q infinity is equals to 0. Similarly, if I substitute q equals to minus infinity, in that case, you can see this integration limit will go from minus infinity to plus infinity. And that reflects that we are actually integrating this PDF curve from right from minus infinity to positive plus infinity. Okay, so we know that the area under the PDF curve is equals to 1, and therefore this probability is going to be equals to 1. So here you can see this particular q function curve, that here we have onto the y-axis, onto the x-axis, we are having the different values of your y, and here we are having the value of your q function qy. So when this y value is approaching towards infinity, this qy is actually approaching towards 1. Okay, so this value is approaching towards 1, that we can see. Okay, and when this y is tending towards infinity, positive infinity, then this q function is approaching towards 0. Right, and because we know that because this is our PDF curve which is symmetrical about 0, so if we take this right half, okay, right half of this particular curve, then the area of this particular curve will give you the half of the probability. Okay, so this probability will be 0.5, and another half, if you see this negative half, then it will be again 0.5. So therefore, when we substitute q equals to 0, we are going to get this value equals to 1/2. Okay, so this way you can understand this q function. Now, as I already explained about the symmetry, what we can have is, because of the symmetry property, if we calculating this probability p, okay, that the x will be greater than x1. Okay, if we choose any positive value x1 at this point, if we calculate this probability, okay, then this area will be same as if we calculate this particular probability that x is less than minus x. So if we take any corresponding points at this point, and if we calculate this area, okay, that will be same as this particular area, right? Because of the symmetric of your curve. So therefore, what we can have is we can always get this particular probability. If we want to plot, if we want to get this q minus y, let us say, okay, if we want to get this q minus y, the meaning of q minus y is that what is the probability that this x will be greater than minus y. Okay, so if we want to calculate this probability, what is the probability that this random variable will be greater than minus y, then it means that we are interested in calculating this entire area. Okay, the entire just right half of your x equals to minus y. So this area we want to calculate. So another way of calculating this area is to what we can do is, because the total area is going to be 1, so if we subtract this area from 1, okay, this is small area from 1, then we will be able to calculate this entire area. Okay, so that we can that we have written over here, this 1 minus what is the probability that this random variable x will be less than minus y. Okay, so if we subtract this portion, then we will be able to calculate this particular probability. And as we know that due to the symmetry, this probability that x will be less than minus y is same as the probability that this x will be greater than y. Okay, so this probability will be also equal to this probability, and therefore this expression q minus y we can written as 1 minus q y. Fine. So this way you can correlate and you can also observe this symmetry of the curve. Okay, this symmetry of the curve is actually you can also observe from this particular relation. Okay, so now we can also represent this cumulative distribution function in terms of your q function, right? So how it can be represented, because this fx is representing you what is the probability that this capital X will be less than equals to X. Okay, then if we subtract, okay, if we subtract this probability, because qy represents you the probability of x greater than y. Okay, then obviously if we subtract this probability from 1, okay, then obviously we are going to get this particular probability, and therefore this is our relationship between the CDF and our q function. Okay, right. So now here you can see, if we wish to plot the this CDF, okay, for the given this standard Gaussian function, then obviously we have to subtract this curve from 1. So if you subtract this particular curve from 1, this curve we are going to get. Okay, this will be the curve that we are going to get. So I have already explained you that this cumulative distribution function is always be a increasing function of x. So here we can observe that when the x is increasing, this CDF graph is also increasing, and it is attaining its maximum value equals to 1. So now we are going to look the more general representation of the Gaussian random variable. Okay, so the more general representation of the Gaussian random variable is this. It is pxx, which is equals to 1 by sigma root 2 pi e to the power minus x minus m whole square by 2 sigma square. Okay, so if you make a comparison from the previous case, okay, so here this general representation represents that it is having the mean value equals to m, and there is a variance sigma square. Okay, so if you make a comparison for your standard Gaussian function, okay, if you see this standard Gaussian function mathematical expression, here the mean value is actually 0. Okay, here you can also observe that this curve is actually symmetrical about 0. So its mean value is equals to 0, and its variance is also sigma square equals to 1. Okay, so that's why it is known as unit normal distribution function, or it is called as the standard Gaussian function. Okay, but this is the more general representation. So we can have any other values of your variance sigma square, or we can have any other value of your mean value other than the 0 value. So in that cases, this Gaussian distribution will have this type of nature. Okay, so this nature will remain Gaussian, you remember, but it is now shifted version. Okay, it is shifted towards means this particular curve is now symmetrical about this mean value. Okay, this is our mean value m. So this mean value can be positive value, it can be a negative value. So based on the value of mean, just we have to make a shift in the curve. Okay, so here sigma square value going to decide whether this curve will be a very narrow curve or it will be a very wide curve. Okay, it can be a very narrow curve, remember. Okay, based on depending on the value of sigma square. So if sigma is quite large, okay, that time you can see what is the variations, right? So it can be a very wide spread, right, around the mean value, or it can be a very narrow spread around the mean value. So now here you can see this is our CDF value. If we integrate this function, okay, then we can get this particular CDF, right? So here what we can do is we can represent this CDF value in the terms of Q function again. So to do that, we have to just make a certain assumption. If we assume this x minus m divided by sigma equals to z, then we can calculate that this dx will be equals to sigma dz. Okay, and if you do this simple manipulation, you will be able to get this particular expression. Okay, this fxx will be equals to 1 by root 2 pi, and this integration limit is minus infinity to x minus m by sigma e to the power minus z square by dz. Okay, so now if we see this expression, okay, then what we can do is we can represent this fx in the terms of q function, right? So here this will be your x. So I have already explained fxx is equals to 1 minus qx. So here the x value is this x minus m by sigma. So this cumulative distribution function can be represented by this particular expression, right? So this will represents you that the random variable x will be taking a value less than or equal to x. Okay, so if we have the q function table, we can directly calculate what will be this probability for the given values of m, sigma, and x, right? So and now there is one more function which is known as the error function. Okay, so that we have to see. So before that, you can also see this random variable x can be greater than x. Okay, so that probability you can calculate by following this particular expression. Okay, so there is one another function which is known as the error function. Okay, so we have to see this relationship between the q function and error function, because in many of the problems you will find that this q function may be mentioned in terms of error function. So normally I have till now I have already explained you what is the general Gaussian PDF mathematical expression, and I have also explained you what is the standard Gaussian function. Okay, so now to define the error function, okay, the Gaussian distribution normally will have the mean value equals to 0 and the variance will be equals to 1 by 2, right? So this is the condition for defining the error function. Okay, so normally if we substitute this condition, mean equals to 0 and variance equals to half into this particular expression, so this variance equals to half means it is sigma square is equals to half. Okay, so if you do this substitution, you will get that this Gaussian distribution will have this particular mathematical expression. Pxx will be equals to 1 by root pi e to the power minus x square. And you remember that this distribution, this mathematical expression is a little bit different from your standard distribution, because in the standard Gaussian function, the mean value was 0, but the variance was equals to 1. That you remember, okay? But here, while defining the error function, it is a very important difference between the two that you have to remember. Okay, so this error function will have the variance equals to half. Okay, so this error function mathematically defined as it is we have to do the integration. Okay, this is our PDF value pxx, so we have to perform the integration again from minus x to x. Okay, so you see in the case of CDF, when we are calculating the cumulative distribution function, we perform the integration from minus infinity to x. While calculating the q function, we are performing the integration from y to infinity. But here, while calculating the error function, we are performing this integration from minus x to x. And our PDF is also having a different form a little bit. Okay. And now, obviously, this integration is actually representing what is the probability that our Gaussian random variable will be taking the values in between minus x to plus x. Okay, this is the probability. So this error function represents you the probability that this random variable will be in between minus x to plus x, right? So this is the probability. This is the different probability from your q function. Okay. So now this q function, because we know that this curve is symmetrical around 0. Okay, so due to this symmetric property of the integration, we can integrate this curve from 0 to x, and we can have the factor 2 multiplied over here. Okay, so this is the error function definition: 2 upon root pi 0 to x e to the power minus x square dx. And we can again define another function which is known as the complementary error function. Okay, and that complementary error function will be defined as 1 minus error function x. So obviously, if error function x represents the probability that this random variable x will be in between minus x to x, then this complementary error function will represent what is the probability that this x will be less than minus x, as well as it will be greater than plus x. Okay. So this is your complementary error function. So if you write this probability, and this can also be written mathematically as 2 by root 2 pi. Uh, this integration will go over x to infinity, okay, because we are calculating the probability that the x, this random variable x will be greater than x, okay. So e to the power minus y square dy. So this will be our complementary error function. So now we have to try to correlate between the complementary error function or error function with Q function, how these two things will be related. Okay. So if you see the definition of your Q function, this Q function is defined as 1 by root 2 pi, and this integration is going from y to infinity e to the power minus x square by 2 dx. You remember that here we are taken the distribution as equals to standard Gaussian distribution. Okay. So now what we can do is to establish the relationship between the two. What I can do is I can make this substitution. I can take this y and I can substitute y equals to u by root 2. Okay. So if we do this small substitution over here, okay, you can see that this dy will be equals to du by root 2. Fine. Similarly, if you make this substitution when y tends to x, then this u will tends to x by x root 2. Okay. Similarly, when y tends to infinity, and then u tends to infinity. So if you do this simple manipulation, then here you can see this error function x. Okay, this can be written in this form. Okay, so this is 2 multiplied with 1 by root 2 pi. Okay, and after substituting these limits, this limit will change from x root 2 to infinity, and this value will be becoming e to the power minus q square by 2 du. So here you can see this term, okay, this term. So this term is nothing but your Q function form, okay. This is the same as your Q function, whatever you have written over here, okay. This is the same definition, except that here we have this dummy variable u with respect to for your integration, and here we had the x, okay. And here this y is having this value equals to x root 2. So therefore, what we can do is we can write this complementary error function, which is equals to 2 multiplied with q x root 2. So this way, this is the relationship between your complementary error function with your q function. So if you wish, you can also do it other way around. So what we can do is here we can substitute, we can make substitution for your x, okay? And here you can substitute x equals to u root 2. As we have replaced y equals to u by root 2, here you can make the substitution x equals to u root 2, and you will be able to show this particular relation. Okay, you will be easily able to show this relationship that this qx will be equals to a half of error function, complementary error function x by root 2, which is same as 1 by 2, 1 minus error function x by root 2. So try to get this relationship the way I have done here. Okay, the similar way, just you make this substitution, x will be equals to u root 2, and then you try to change the limit, and you will be able to show that this qx will have this particular form. Right. So now I will show you this Q function table, which is normally available in the menu of the books. So suppose if you want to calculate any values. So here I will just show you this example. So suppose that if we want to take this value Q, if we want to find Q 5.36, okay, let us suppose if we want to find the value of Q 5.36. So here you can see here we are having this values like 0, 0 0.1, 0 0.2, 0 0.3. This table is going up to 3. Okay. So if we wish to calculate, suppose if I don't, because I have not taken the complete table here. So here we can take the maximum value, which is equal to 3.09, right? So if suppose if you wish to take any other value, okay, suppose if we wish to take, let us say 5.1 point, and let us suppose if we want to take 1.33, okay. So how to take this value, how to read this value from this table Q 1.33. So here you can see this X value is 1.3, okay, and here it is 0.03. So this value will be corresponding to Q 1.33. So this way you can read this table. So if you read this data, okay, this data is corresponding to Q 0.1. This value is corresponding to Q 0.11. Okay, this is your second digit, right? After your decimal point. Fine. So the similarly, if you see this particular data represents you Q 0.5 2. Okay, it will be 0.52. So this way you can read this table and you can get any values of your Q function, right? Now I will also discuss one small another topic, which is your uniform random variables. So there may be a certain chances that the certain random variable will have the uniform distribution. Okay, so normally if it is having a range between A and B, then obviously this A and B will have its uniform distribution. The probability distribution among any random variable in any outcome of the random variable between A and B will have the same probability, and therefore it is having the uniform distribution, right? So normally its probability density function will be constant. You remember that it will be constant over the given interval in which this distribution is being defined. So we know that because the area under the curve in the PDF should be equals to 1. So because here the width of this particular distribution is B minus A, then obviously to this area to be equals to 1, this height should be 1 upon B minus A. So that if you multiply this to, you are going to get this area equals to 1. So this is the basic definition of this uniform random variable. So wherever it is required, you can just follow this equations, okay, for your uniform random variable. So we stop here today. Okay, so we discuss some more topics in some other lectures. So thank you for watching this video. Stay connected with the channel.